Hey there, STAT216 students. Welcome to another RStudio tutorial video. In this video, I'm going to show you how to make calculations about binomial random variables in RStudio. The flavor of this video will be very similar to the last one I made about geometric random variables, and the slides will look very familiar as well. But there's a crucial difference that I'll try to emphasize and highlight a few times throughout the video. Without further ado, let's dig right in. So, like before, when we were talking about geometric random variables, we want to discuss Bernoulli experiments, but this time we'll go a little bit more quickly. The reason we're talking about Bernoulli experiments in this section is because, like the geometric random variable, binomial random variables are built off of sequences of Bernoulli experiments. So what is a Bernoulli experiment? Well, it's any experiment or random process with only two outcomes. And remember, we typically call these outcomes success and failure. We denote the probability of success by P, which means that the probability of failure has to be 1 minus P. We assign a 1 to success, a 0 to failure, and that gives us a Bernoulli random variable. And going through some calculations gives us the expected value, or the average outcome of a Bernoulli random variable is P, and the standard deviation has this nice formula that you can see there. Great. Remember our example from last time. If we roll a die once and count a success as getting a 4 and anything else is a failure, then this determines a Bernoulli random variable with probability of success equal to 1/6 and probability of failure equal to 5/6. So what is a binomial random variable then? Like in the geometric random variable video, we're going to motivate this with an example. So instead of rolling a die until we get our first success, we want to fix the number of trials that we have. So we're going to consider rolling a die 12 times and then count the number of 4s we get after rolling the die 12 times. So we have a fixed number of trials and we're counting the number of successes. And that is the big difference between a geometric random variable and a binomial random variable. When you have a geometric random variable, you perform these Bernoulli trials, these independent identical Bernoulli trials, until your first success. When you have a binomial random variable, you have a fixed number of trials of independent identical Bernoulli random variables, and you're counting the number of successes. So you have a fixed number of trials, count the number of successes, and that determines something that we call a binomial random variable. So if we have a binomial random variable with n trials, then the probability of witnessing exactly k successes can be described by this formula here, where we have n choose k times p to the k times 1 minus p to the n minus k. Now, if you remember from lecture, this has a pretty nice interpretation. This is the probability of one scenario with exactly k successes. So it's the probability of one scenario with k successes. You could think of all k successes occurring first, and then the remaining trials being failures. That's the probability of this particular event. But if you shuffle up your successes and failures, the probability of each particular scenario stays the same. Now, n choose k has a nice interpretation. It's the number of scenarios with exactly k successes. So it's the number of scenarios with exactly k successes. Let's think of an even more simple example than our die experiment. If we flip a coin twice and count the number of heads. Let's try to find the probability of exactly 1 heads using RStudio, and we'll go about this in a sort of naive way first, and then we'll use the fancy distribution commands like we did in the last video. So what is this going to be? If we want to find the probability of 1 heads out of 2 flips, what's this going to be? To choose 1, 0.5 to the 1, that's the number of successes. 0.5 to the 1, that's the number of failures in this case. So if I wanted to calculate this in RStudio directly, what I would do is choose 1 times 0.5 squared, 0.5 to the first power times 0.5 to the first power. The choose command is just choose. So if you want to do n choose k, it's choose n comma k in RStudio. And no surprise, we've looked at the probability of 1 heads many times in previous examples, and we see that the probability of exactly 1 heads out of 2 coin flips is 0.5. Great. If we had larger numbers, or if we just wanted to do more calculations, going about making binomial calculations in this way could get a little tedious. There's kind of a lot of typing involved. So what we'd hope for is a nice, easy way to use RStudio to make calculations about binomial random variables. And just like with the normal distribution and the geometric distribution, there's a command built in that's built off of referencing the binom distribution. Binom, of course, means binomial distribution. And the binom distribution has P, the P prefix, D prefix, Q prefix, and R prefix. Just like with the the geometric random variable, we'll primarily use D binom and P binom. Again, P binom gives us a percentile, so it's the probability of at most k successes out of n trials. And this means the probability of exactly k successes out of n trials. So D binom gives us the probability of exactly k successes, and P binom gives us the probability of at most k successes. Now the arguments that you chunk into these commands are the number of successes followed by the number of trials in your binomial experiment followed by the probability of a success. Great. Let's actually see how we can use these in the context of a couple problems. So now we're going to roll a single die 12 times and count the number of 4s we observe. What is the probability that we get exactly 5 4s? Let's just do a quick check to make sure that we actually have a binomial random variable. Do we have a fixed number of trials? Yes, there are 12 trials. Are our trials independent, identical Bernoulli trials? Yes, because we're rolling a die 4 times. They're independent, and they're identical because we can think of it as being the same die. And what are we doing? We're counting the number of successes. In this case, n is 12, k is 5, because we want to find the probability of exactly 5 successes, and the probability of success, again, is 1/6. To write it all out, we want the probability of observing exactly 5 4s out of 12 die tosses. And to use RStudio to do this, we'd want to do D binom. Let's go back to the slide to remember what to do here. D binom, number of successes, number of trials, probability of success. So we do D binom 5, 12, 1/6 here. D binom 5, 12, 1/6. see I made a mistake. NaN's produced and not a number. That's because my probability of success wasn't a probability. Sorry about that. So I put a 1/6 there, and we get about 3%. So if you roll a die 12 times, there's about a 3% chance you'll get 5 4s. Not particularly interesting or useful, but it is a fact. Let's also verify the last calculation we made. We said the probability of exactly 1 heads was 0.5. So if we do D binom, if we want the probability of 1 heads out of 2 coin tosses, it'll be D binom 1, 2.5. There we go, we get 5 again. So D binom is actually doing exactly what we hope it is. The next example will show us how to use P binom. So we roll a die 12 times, count the number of 4s again. What's the probability that we get at most 5 4s? So now we want to find the probability that X is at most 5. Again, that's this guy coming in up strong. We want to find the probability of at most 5 4s. So what would we do? Since it's a percentile, whenever you have something less than or equal to something, that's a percentile. So this is going to be a P binom. 5, 12, 1/6 again. So P binom 5, 12, 1/6 because it's the number of successes, maximum number of successes, number of trials, followed by the probability of success. P binom, actually I'm just going to scroll up and change my D to a P. I didn't change the arguments there, so we want 5 successes, at most 5 successes out of 12 die rolls, and a probability of success is 1/6 here. So the probability that you get at most 5 4s is about 99%. So you're almost certain to get at most 5 4s. This makes sense. We expect, if we're rolling a die 12 times, we expect about 2 4s on average. Any more than that, and things start to get relatively rare. What was the P binom 1, 2.5 telling us? That's the probability of at most 1 heads out of 2 coin flips, and there's a 75% chance of at most 2 heads out of 1 coin flip. No surprise on that one either. Great. Last example. It'll be similar to the last example from the geometric random variable video, but we want to roll a die 12 times, count the number of 4s again, and we want to find the probability that we get more than 2 4s. So what is this? Writing out the probability, it's the probability that X is greater than 2. We want to find the probability of more than 2 4s. Now, what do we do here? This is the same, again, since this is not a percentile, but it's close to a percentile. In fact, it's the complement of a percentile. We want to employ the complement rule here. So it's 1 minus the probability that X is less than or equal to 2. So this is 1 minus P binom, the number of trials, the number of successes, the number of trials, and the probability of success. And since this is the complement of a percentile, we know that we can also use the lower dot tails function. So this will be the same thing as P binom 2, 12, 1/6 lower dot tail equal to false. Let's go through and actually make those calculations. So if we do 1 minus P binom 2, 12, 26, you get about a 32% chance. So that means that there's about a 32% chance you'll get more than 2 4s if you roll a die 12 times. Let's verify that the lower dot tail equal false command does the same thing. So p binom 2, 12, 1/6, lower dot tail equal to false. Voila, it gives us the same thing. I hope you're starting to recognize a pattern among using these distribution functions in RStudio. They have the same flavor in the very similar implementations. You just change the argument or the parameters of each of the distributions on their own. Thanks for sticking around. I hope this is helpful for making some calculations in your homework and maybe even making some calculations in your life out there in the wild. Enjoy the rest of your day or evening, and I'll see you soon.